Welcome everyone. So today this is lecture 21 of CS229, and the topic for today was evaluation metrics and also some general advice on applying machine learning in practice, in deployment or in production. So we're going to look at a few evaluation metrics, and next once we are through with this presentation, we'll quickly go through some ways in which these evaluation metrics can actually be useful in production. So let's get started. So this is the quick overview of what we're going to be covering in this presentation. First, why evaluation metrics. Then we'll focus on binary classifiers. That will be the a problem setting that we'll spend most time on. Different kinds of metrics, and some general tips on how to choose evaluation metrics, and what to do when in certain scenarios when there's class imbalance, and how certain metrics kind of break down in different settings. So first of all, why are evaluation metrics important? In what we've seen in all the algorithms in this class, we define some kind of a loss function and minimize the loss function with respect to the parameters to minimize the loss on the training data. However, these loss functions, it's not always clear whether these loss functions are meaningful in terms of the real world use, right? For example, the loss function may or may not capture some kind of a business goal you have, right? If your business goal is to improve your revenue or your profit, like your loss function may or may not always reflect that, right? So it's always important, that's why evaluation metrics, which are like this secondary measure that you have on your model performance, become extremely important, right? Evaluation metrics also helps organize your team effort towards some kind of a business target, right? So usually it's common practice to define some kind of a dev set, and the team which is working on improving the model performance strive to improve the evaluation metric on that dev set, right? You want to start thinking about the evaluation metric as something distinct from the loss itself, right? And it's also useful to kind of quantify the gap between the desired performance and the baseline, right? So it's easy for, say, a product manager to define what the evaluation metric should evaluate to on your dev set, but it's hard for someone to say what the loss value should be on a dev set, right? So evaluation metrics are useful to measure how well your model is doing in terms of your desired performance level, right? So it's useful to quantify that gap. And it also, you can use it to see the gap between the desired performance and the baseline. Baseline is generally the first attempt that you come up with, some kind of a simple model. That gives you a sense of difficulty of the overall project that you're starting with. If the gap between the desired performance and the baseline is a lot, then probably it's a challenging task. And similarly, you can also measure the gap between the desired performance and the current performance, which kind of gives you a sense of how much more progress is left to be made, right? And it's also useful to kind of keep track of how our performance is improving over time. When we started off, we were at 60% accuracy. 3 months in, we are at 75% accuracy. Our ideal our target is 85% accuracy. So that it gives you a sense of how much progress you've made towards the end goal. It's also useful for lower level tasks such as debugging, right? You want to do some bias variance analysis on your model to improve your model performance, and evaluation metrics are useful there as well. So ideally, your training objective, your loss function, should reflect your business goal, right? But that's not always possible. For example, if you care about accuracy, it's very hard to train a model by using accuracy as the loss function, right? So accuracy is not even differentiable. It ends up being a very hard combinatorial problem, and it's using accuracy as your loss value as your loss function. Generally just does not work. You can't get gradients out of them, etc. right? So ideally we would want your metric to itself be the loss function, but that's not always feasible. So that kind of makes it necessary to do this measuring this evaluation metric in parallel as we are developing the model beyond just the loss function. So we're going to limit for most of this presentation. We're going to stick to binary classification in a supervised setting. So think of X as an input. X could be an image. It could be an email. Y is a binary output. If it's an image, you want to tell whether there is a pedestrian in that picture or not. If you're in the context of say a self-driving car, it could be whether a given text is spam or not. So Y is think of Y as binary. The model output is Y hat, right? And this Y hat can be of different types. For certain kinds of algorithms, for example, we did not cover these in the course itself, but algorithms like k-nearest neighbor or decision trees, the output of the algorithm is directly the class prediction itself. The output is the class directly, right? And there are other kinds of algorithms whose output is some kind of a real valued score, like support vector machines or logistic regression. In logistic regression, the output was the probability of Y being 1, right? It's a real value. It's not a class directly. And with support vector machines, you would output the margin, right? How far from the margin separating hyperplane is the example that we are looking at? Is it to the left of the margin or to the right of the margin? Right? So, and those are real values. And in these score-based algorithms, where we output some kind of a real value, it becomes necessary to choose some kind of a threshold. And once you pick that threshold, you can convert your model into a classifier, right? And these score-based models are the one we'll be looking at in this presentation, right? So think of this is kind of the mental picture you want to have. So the line here from 0 to 1, think of it as the range of probabilities that can be output by the model. Right, 0 indicates the predicted probability is 0, and 1 indicates predicted probability is 1. So the green dots represent positive examples, and the position of the dot is the probability assigned by the model for that example. Right, so the green dots are the positive examples, gray dots are the negative examples, and this by placing them on a line like this, we are kind of defining a natural order on the predictions, right? And it's always good to first have a look at this kind of rank order of your examples in your dev set before you start debugging your model, right? This gives you a good sense of what your model is kind of doing in a big picture. A few more some metrics that are or some terminology that are useful. So prevalence is a term that refers to the fraction of examples that are positives, right? So that's a standard terminology. So if you're in a situation where you have an equal number of positive and negative examples in your data, then the prevalence is 50%. Right? If you have, say, 10 positive examples and 90 negative examples, then your prevalence is 10%, 10 over 10 plus 90. All right.
Is prevalence defined on the data set, or is it the property of our model that
Good question. So prevalence, the question is prevalence a property of the data, or is it a property of the model? Prevalence is totally a property of the data that you have. It's just a fraction of positives that you have. So here, a good point is that here, when we are counting positives and negatives, we are counting the ground truths, not the predicted probabilities. Right? Any questions on this? And it's this prevalence term that allows us to kind of decide whether we have something like a class imbalance problem. So a class imbalance problem is when one of the classes is either too many or too little compared relative to the other class. If out of 100 examples in your data set, if 2 are positive and 98 are negative, then you generally call it a class imbalance problem. There's no agreed upon threshold to decide whether you have a class imbalance problem or not. But as a thumb rule, if one of the classes, if the prevalence is less than 5% or 10% or more than 90% or 95%, then it's reasonable to think of the problem as having low prevalence. And sometimes, for example, if you're in the problem of say detecting credit card fraud, right? The volume of non-fraud transactions is probably so high that in those kind of problems, prevalence will be really, really small, like much smaller than 1%. Okay. So we started with the score-based view. I'm going to go back to the slide to compare again. So we started with this line where we've placed all the examples by ranking them based on the predicted probability of the model, right? So the green and white are property of the data. Their positions is the property of the model. The model assigned probabilities for each example, and that's how we started it. And this by itself is not a classifier, but once we decide a threshold, right? Once we have a threshold, let's say we set the threshold equals 0.5, now we have a classifier. Every example that's above the threshold line is classified as positive, whether it was positive or not. Every example below the threshold is classified as negative, right? So the vertical axis is our prediction. Anything above the 0.5 threshold is predicted to be positive. Anything below is predicted to be negative. And the true label is on this. We kind of separate them horizontally. So to the left is those examples that truly are positive, and to the right are examples that truly are negative. Right? And here we've chosen a threshold to be arbitrarily 0.5. And only once we choose a threshold does a score-based model become a classifier. Until we decide a threshold, it's not a classifier, right? It's just assigning scores or probabilities. After we choose a threshold, we get a classifier, right? So what did we do here? We just summed up the number of examples in each block, right? So on the top left is the examples that were actually positive, and we also predicted positive. And similarly, on the right top, we have examples that were predicted positive but were actually negative, right? And this kind of a matrix is called a confusion matrix. And that's just a standard terminology, right? So a few properties of the confusion matrix. The first is that the total sum of all the 4 squares is fixed, right? Because the number of examples we have is fixed, right? Also, the column sums are also fixed, right? The sum 9 plus 1 and 2 plus 8 in this case will always be fixed because they are the number of positive examples we have and number of negative examples we have. What can change in a confusion matrix is the based on what threshold we choose and the way in which the examples have been ordered by our model. The fraction of the left column that goes up and below and fraction of the right column that gets split up and below, that can change, right? So the total sum is fixed, the column sums are also fixed, right? And basically, by looking at a confusion matrix, you kind of judge the quality of your model depending on how heavy the diagonals are and how light the off diagonals are, right? So you want the diagonals to be heavy, which means you want the examples that were positive to be predicted positive and that were negative to be predicted negative, and you want the errors, examples that were positive or predicted negative to be low, and similarly that were negative and predicted positive to be low. So another observation to make here is that a confusion matrix does not give you a scalar value, like it's a set of 4 numbers, right? Given 2 different confusion matrices for the same model in the same data set, it's hard to it's hard to compare them and say which confusion matrix is better, right? They're not scalars, they're like sets of 4 numbers. You can't compare them unambiguously. Right? And so we start extracting comparable metrics out of this. So the top left, that the number in the top left quadrant is called true positives. So they are true positives is a confusing term. So you might want to it's true positive sounds like what is the ground truth, but unfortunately the term true positive refers to examples that were actually positive and were also predicted to be positive, right? So in this case, true positive is 9, right? And so on the right hand side, we're going to start extracting these metrics or statistics out of this confusion matrix. Next, true negatives. Again, true negatives is the number of examples that were actually negative but also predicted to be negative. Here, trueness refers to that our prediction was true. That's what it basically means. So true positive means it was predicted positive and we got it right. True negative means it was actually negative and we got it right. Right? So trueness kind of lies on the diagonal. We want the true positives and true negatives to be high. Right? So false positive is examples that were predicted to be positive, but our prediction was wrong, a false prediction. So false positives are examples that were actually negative, but we predicted them as positive. And similarly, false negative are examples that were actually positive, but we predicted them as negative. And these two are false positives and false negatives are kind of two very different kinds of errors. And depending on the actual application that you are working on, false positives and false negatives may have very different kinds of impacts. Right? It's very common that the kind of weight that you want to assign to false positives and false negatives will generally be asymmetric. So we have basically extracted 4 metrics out of this confusion matrix so far, and this false positive and false negative are they also have some other terminology. For example, they're also called type 1 and type 2 errors, right? So type 1 error is when is a false positive when you don't have a certain condition, but you predict that you have that condition. You don't have the Y label is false, but you predicted Y to be true, right? Similarly, the type 2 error is commonly called is another name for false negatives, where the true condition is true is 1, Y equals 1, but you predict Y equals 0, right? This is I found this on Twitter on someone's Twitter page, but I could not find the source of the image to cite it, but it's a funny image. Right? So back to the slide. The larger takeaway is that depending on the kind of errors you make, the kind of impact that false positives and false negatives have can be very, very different, right? So if you were to, for example, prescribe some kind of a medication, then false positives and false negatives can have different kinds of effects, depending on whether so for example, if you want to prescribe a medication based on whether a person has a disease or not, and if that medication has no adverse side effects when given to an ordinary person, then you are much more likely to worry about false negatives, because you don't want to lose out on people from getting that medication. So you want all the people who have the patients who have the condition to be predicted so that you can give the medication. Right. So another metric is accuracy. Right. So accuracy is basically what is the fraction of all the examples, no matter what class they were, that we predicted right, that we got them right. Right. So accuracy is generally kind of the trace of the matrix divided by the sum of all the elements. And if you want to optimize your model for accuracy, then it corresponds to actually using something that's called the 0-1 loss. Right? 0-1 loss refers to you have a loss of 1 if you got the answer correct, and you get 0 if you got it wrong. Right? So optimizing for 0-1 loss, which is very hard to do in practice because it's not a differentiable loss, that's accuracy. Right? Now there is another metric that's very important called precision. Right? So accuracy and precision in our day-to-day language, we might kind of use them interchangeably, whether we are accurate or precise. But in a statistical setting or in a machine learning setting, the two have very, very different meanings. Right? So accuracy is what fraction of all the examples that we got right, whether they were positives or negatives, doesn't matter. Whether we predicted them right or not, that's what accuracy measures. However, precision means among the examples that we predicted to be positive, what fraction of them were actually positive. Right? So in precision, we are kind of limited to the top half of the confusion matrix. Right? So the top half of the confusion matrix is characterizing all the examples that were predicted to be positive. And now precision measures what fraction of the predicted examples were actually positive. Right? And there's another name for precision. It's also called PPV. So PPV stands for positive predicted value. So precision is also called PPV, positive predictive value. Right? Yes, question?
So when you train a model, you can only look at the loss function and then train it based on the loss function. And if you want to give a higher weight to, let's say, false positives, you want it to be overly cautious. How can you quantify that in your loss function?
Yeah. So the question is, if you worry a lot about false positives, how do you kind of quantify that into your loss function? Because your loss function is just a loss function. We'll touch upon that in some of the future slides. But that's a good question. That's the kind of questions you should be thinking about, because our loss function is our loss function kind of asymmetrically treating false positive or false negatives? If not, should it? How do we do it? That's definitely a very good question. Right? So that's precision. So precision is among the examples that we predicted to be positive. What fraction of them were actually positive? And you can see that the precision is all these metrics that we've seen so far. True positive, true negative, false positive, false negative, accuracy, precision. These are all metrics that actually depend on the threshold that we choose. Right? So these are all threshold sensitive metrics. Right? Similarly, there is something called sensitivity. Sensitivity is also called recall. Right? So precision. Recall is also called sensitivity. So in recall, what recall measures is, if we were to use this classifier in deployment, what fraction of all the actual positives are we going to recover? Right? So if let's say there are 100 patients who are out there, and some fraction of them, say half of them, have a certain condition. We run all the patients through our model, and our model is going to predict true or predict positive or negative for each example or each patient. And finally, if we look at all the patients who actually had the condition, what fraction of those patients did our model predict as positive? Right? And this is called sensitivity. So the term sensitivity kind of comes from, I think it comes from epidemiology, where how sensitive is this test for detecting a certain condition. Right? That's exactly what this is measuring. So in this case, say there were a total of 10 positive examples. I'm counting the examples on the left half of the confusion matrix. And sensitivity is measuring the top number, 9 divided by 9 plus 1. So like, so the sensitivity here is 90% because we were able to correctly, or we were able to recover 9 out of the 10 positive examples. So one thing to note here is that sensitivity is kind of staying agnostic to everything on the right. So we are only focused on what fraction of patients were, or what fraction of examples that were actually positive. So we are conditioning on just the positive examples and checking, what fraction of them we were able to recover. Right? This is completely agnostic to what happened to the examples that had a ground truth of negative. We are just ignoring that half of our data set completely. Right? So one way to another way to think of this is if you want to have perfect recall, right? If you want to have 100% recall, then no matter how good or bad your model is, just choose a threshold of 0, right? If you choose a threshold of 0, no matter how good or bad your model is, you will get 100% recall, right? And similarly, if you want to, in the previous example over here, this was about precision. If you want to have a model that is 100% precise, right? Then all that you want to do is choose the threshold such that the threshold just classifies the top one example to be positive, and you will get 100% recall. Right? So viewing these metrics in isolation generally does not kind of capture the true performance of a model. Right? So what we'll see this shortly, that most of the times we are trying to balance off precision and recall in some way, because we don't want our metric to be blindly placed all the way at the bottom to maximize our recall. Similarly, we don't want our threshold to be blindly placed all the way at the top to just get good precision numbers. Yes, question?
Why is the green part of the matrix, the top of the matrix, isn't it the left part of the matrix that we are interested in with this matrix?
So the question is, why are we looking at the top half? We are interested in the left half. Yeah. So the left half of this matrix are the examples that have a ground truth to be positive, right? But our model, when it's making a prediction, it does not know, what the ground truth is, and it's going to assign some kind of a probability. And depending on what threshold we choose, right? So in this case, threshold was 0.5. We classify everything that the model classified, as above 0.5 to be, we predict them to be positive, right? We don't know what the ground truth is. Yes, we are interested in the left half, but the only way we can classify them is as top half and bottom half. Good question. So that's recall. Similarly, there's something called negative recall. So negative recall is basically doing the same exercise as recall, but we do it on the right hand side of the confusion matrix, which means so negative recall is calculating of all the examples that had a true or the actual label to be negative, what fraction of that subpopulation did the model actually correctly classify as negative, right? And in negative recall, just like positive recall, we kind of stay agnostic to the left half of this picture, right? We don't care how correctly or incorrectly the model performed on the ground truth equals positive. We just consider the examples on the right hand side and see what fraction of the actual examples, actual negative examples, did the model correctly classify as negative. And negative recall has another term, specificity. Right? Right? So negative recall is specificity. And you can start kind of combining these individual scores into, in certain ways. For example, there's something called the F score or the F1 score. So F1 score is so F1 score is basically the F1 score is the harmonic mean of precision and recall. So 1 over F1 is 1 over precision plus 1 over recall. Right? So you can combine your precision and recall into a single number called the F1 score. Similarly, there is something called, just like the F score, there is something called the G score, which is the geometric mean of precision and recall. So, so the G score, you have the geometric mean. So it is log G equals log precision plus log recall. So it's G is square root of precision times recall, and F score is therefore precision times recall over precision plus recall. Oh, sorry. No, it's not square root, obviously. Sorry. So G, so G is, so ignore this, G is actually, so this is the correct, it is the geometric mean. So I guess I missed a half over there. Yeah. Yes, question?
When you look at these quantities, like F1 and G1, how do you make sense of what's happening with data?
Yeah, so what do these F scores and G scores kind of represent? So as we saw before, just looking at precision or just looking at recall is insufficient, because you can just fool the model by having 100% recall by setting the threshold all the way to 0, right? But if you were to do that, you will take a hit on precision, right? And similarly, if you maximize your precision to 100% by setting your threshold all the way at the top, so that you just classify that one correct example as positive and just ignore everything else, your precision will be 100%. But your recall will be really low, because you've recovered only one out of all the positive examples that you have, right? So it is some way to kind of balance the two in some way. So the geometric mean and harmonic mean are kinds of means where if any one of them is low, then the entire mean is low, which is not the case with arithmetic mean. So arithmetic mean will just is pretty robust to stay high, but geometric mean will just bring down your value to be really low if either one of them is low. So these are just two different ways of kind of combining the two metrics in some way. Yeah, it's another way to say what is the min of my precision and recall, right? That's what the geometric mean is kind of doing under the covers. Yes, question? So the question is, why not just focus on accuracy? Why are we doing all these other things? We'll come to that.
Captures both precision and recall to some degree.
So the question is, does accuracy capture precision and recall in some way? Maybe not. We'll see more why accuracy is not always the right thing to look for. Right. So in examples when in situations where your data is well balanced, you have an equal number of positives and negatives, then accuracy and precision and recall will be more or less kind of similar. But if you have class imbalance, let's say just 1% of all your examples are positive, right, and 99% of your examples are negative, then if you have a model that just says no to everything, it'll get 99% accuracy. Right, so in class imbalance situations, these precision and recall kind of metrics will be much more robust from getting fooled, whereas accuracy can be easily fooled in low prevalence scenarios. Right, so that's F score. And now, so everything that we've seen so far are specific to this chosen threshold, right? So our model did the ranking, and then we chose a threshold, and out of this, once we chose this threshold, we got this confusion matrix, and from that confusion matrix, we extracted all these threshold specific metrics. Now, what happens if we change the threshold from 0.5? Let's say we move it up to 0.6. Right? If we were to choose a different threshold, then some of these numbers changed. So the metrics that changed are highlighted in red. So I'm going to go back one slide for you to compare again. Right? So this was with threshold equals 0.5. With 0.6, we see that the true positive changed, the true negative did not change. Similarly, the false negative changed, the accuracy changed, the specificity did not change. So some of them changed, some of them did not change. Right? And now similarly, we can repeat this exercise by trying as many different thresholds as possible. So first of all, how many effective thresholds are in this are there in this situation? For example, choosing a threshold here versus slightly below changes nothing, right? No example was classification of no example changed. So in this kind of situation, the number of effective thresholds we have is 1 plus the number of examples, right? So that gives us all the possible different thresholds that are somewhat meaningful. And so what we can do is basically repeat this exercise of not just checking at 0.5 or 0.6, but check it with all possible thresholds, right? So this is the same ranking, right? The ranking has not changed. Ranking is a property of the model, but a threshold is something that we choose to apply after the fact, right? And for each particular value of the threshold corresponds to each row in this table on the right side, right? And as we change the threshold, we get different values of true positive, true negative, accuracy, precision, recall, and so on. Right? Now, as I said, each row corresponds to each effective threshold, and the table itself is a property of our model. So if our model if we were to take a different model and take the predictions from the other model, the ranking would probably be very different, right? And so this entire table is kind of specific to the model that made the predictions, but each rows within this table depends on what threshold that we chose. And you can make a few more observations in this table. So first of all, many of these columns are monotonic. So for example, true positives starts at 0 and monotonically increases to 10. True negative, similarly monotonically decreases. Similarly, false positive monotonically increases, false negative monotonically decreases. Recall monotonically increases, starts at 0 and ends at 1. And specificity monotonically decreases, starts at 1 and ends at 0. However, there are these other metrics. For example, F1 score, right? There is no strict ordering. It kind of reaches a maximum somewhere at around a threshold of 0.4 or something. Similarly, accuracy also kind of reaches a maximum at 0.45, and it reduces as we go to the extremes, right? So some of them have this kind of monotonic relation where we increase in one direction or decrease in the other direction, and precision is kind of interesting because in precision we kind of keep going up and down, right? So precision, we start at 1, come down to 0.6, go up to 0.75, 0.8, 0.83, and then come down to 0.71. So it's kind of going up and down. And so what we want to do is try to capture the trade-off between these columns in some way, right? So as we saw before, if you want to just maximize recall, just set your threshold to 0. If you want to maximize your precision, maybe just set it at 1 or just below 1. But instead what we want to do is not just look at how the model performs at some specified threshold, but summarize these entire columns in some way. Right? And so that's the question. How do we summarize the trade-off between, say, precision and recall, or specificity and sensitivity? Right? And that's where things like the ROC curves come into picture. Right? In the ROC curve, it's called the receiver operator characteristic curve. It is a trade-off between specificity and sensitivity. Right? So sometimes you may see the ROC curve to be flipped. In some books, or some articles, you'll see it flipped, where on the x-axis you have 1 minus sensitivity, or but it's basically the same, right? And so the ROC curve is this is the plot that you get by scanning the threshold. So I'm going to go back one slide. So 2 slides rather. So as we scan the threshold from 0 to 1, and for each threshold we read off the sensitivity and specificity and plot that point on a graph of sensitivity versus specificity. And as we plot the different points that we get by scanning different thresholds, connect those points as well, and you get this ROC curve. Right? So the ROC curve is giving you the trade-off between sensitivity and specificity as we scan the threshold. So for example, when the threshold is set at 1.0, so you set the threshold all the way at the top, right? Your recall will be 0, right? Your sensitivity will be when you set your threshold all the way at the top at 1, that corresponds to the top left corner. Your sensitivity will be 0, but specificity will be maximum. And as you keep as you keep scanning your threshold down towards 0, you start exploring all these other points. Right? So one way to think of the ROC curve is, so another way to think of it is, let me just, okay. So create a grid. Create a grid where you chop up the horizontal axis into equal sized ranges into as many number of examples you have. So if you have, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's say you have 12 positive examples, right? And chop up the vertical axis into the number of negative examples that you have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 negative examples. Right? And now your model gives you, some kind of an ordering, right? So your ordering looks something like this, right? So positive, negative, positive, and so on. So it's going to give you some kind of an ordering. Now, one way to think of this ROC curve is start from the top left, right, and inspect one example at a time, right? If you encounter positive examples, move right. If you encounter a negative example, move down, right? So first is a positive, we move right. Another is a positive, we move right. Next we got a negative example, we move down. Then we got a positive, move right, etc. And because we have, we can only make 12 number of exactly 12 number of right moves and 13 number of down moves. No matter what order you are, you always start here and you always end here, right? And if all your positive examples are at the top, then your curve will look like this. So it will tend towards the top right corner if most of the positive examples are at the top, right? And so this intuition gives rise to this derived metric from an ROC curve called the area under the ROC curve, right? So the area under the ROC curve is basically this area, and this area under the ROC curve will be high if most of the positive examples, or if all of the positive examples are the ones you encounter first as you start scanning down. right? Because positive examples will just keep you moving to the right. And another observation you can make is that ROC curves always have this, can always be broken down into these horizontal and vertical segments or chunks, and each chunk corresponds to one segment of consecutively occurring positive group or a negative group, right? So you keep moving to the right, so you get one long horizontal chunk if you encounter lots of positive examples, and then once you switch over to some negative examples, you kind of get a kink here and you start moving down and so on, right? So this is the ROC curve, and the area under the ROC curve is generally a useful metric to check how well our model is kind of classifying. Right? If it does a good job of placing all the positives up and negatives down, then the area under the ROC curve will be high. Right? Any questions on this? Good. So a few more observations on ROC curves. So if you have a model that randomly assigns probabilities to your examples, then the ROC curve will fall along this diagonal. Right? So if let's say you have a model, you get an example, and your model, instead of predicting some kind of a probability, it just samples a probability between 0 and 1 in a uniform distribution 0 and 1, and outputs that probability. Then the ROC curve will exactly coincide with this diagonal line. Of course, this diagonal line looks smooth. It assumes you have lots and lots of examples. Otherwise, it's going to be a diagonal line that looks like this. Right. So a random guesser will have an ROC of 0.5. Right. So that's like a low bar for what you should be aiming for with ROC. Right. If your model has an ROC less than 0.5, then your model is basically doing worse than random guessing. Right? That's bad. However, there is if it is doing like really low, like if your model has an ROC of 0.1, that is somewhat good news, because you can just flip the labels and you can get a really high ROC. Right? So staying at 0.5, if your ROC is 0.5, that's bad. You want it to be as high as possible. But if it's really low, you can always just flip the labels, and it will perform pretty well. But of course, that is still disturbing. You should definitely investigate why it is predicting low. Maybe there's a bug somewhere. But yeah. So 0.5 is it should be the low bar when you're looking at ROC values. So if you see read some paper and say the ROC was 0.65, you should not think of the model could have scored 0 to 1 and achieved 0.65. You should think of between see 0.65 as the ratio starting from 0.5 to 1, not from starting from 0 to 1. Right? So something with an ROC of 0.6 is quite close to random guessing. There's another interpretation of the ROC, the area under the ROC curve. So the other interpretation of the area under the ROC curve is, supposing you choose a random example, a random positive example, and then separately you choose a random negative example. Now, what is the probability that in this random pair of positive and negative examples, the positive examples will be ranked higher than the negative example? That probability is exactly equal to the area under the ROC curve. Right? So that's another way to think of the ROC curve. What's the probability that a random positive example is ranked higher than a random negative example? Rank means in this, pick one random positive example. Say it was this green dot. Pick another random negative example. Say it was this gray dot. Right? Those random positive and negative examples get some kind of a score from the model. Were those scores ordered in the correct way? That's what ROC measures. Any questions? So another thing to note is that the ROC curve is agnostic to the prevalence of your data set. Right? So what that means is if instead of 13 examples, you had 130 examples, right? All that means is the granularity of each of the vertical drop would be smaller, right? But roughly speaking, you will still get a similar area under the curve, right? It would just be a little more fine-grained, but the area under the curve will be pretty much the same. So the AUROC is agnostic to the prevalence of the data set. That's something to keep in mind when you're evaluating models, because that's both a strength and a weakness of the ROC curve. That the ROC curve, if you measured your if the ROC curve that is reported to you was measured on a data set that had equal prevalence, but let's say in the real world the true prevalence is very different, then you know that the ROC performance on the real world will still be the same. So that's the good part of it. But the bad part of it is probably the ROC curve is measuring the wrong thing, right? If what it reports is agnostic to the prevalence, then maybe what ROC is measuring is not the right metric, right? And we'll see some of that soon. All right, so that's ROC curves. So there's this. So the ROC curve was the trade-off between sensitivity and specificity. The precision recall curve is the trade-off between precision and recall, right? It's plotted in the same in a similar way as the ROC curve, right? You start with a threshold at 0.1, read off the precision and the recall values. You get a point, and then scan down the threshold a little bit, read the new precision and recall values. That's the next point, connected by a line. Next, bring down the threshold some more. You get a new precision and recall value, plot it and connect by a line, and finally you get a full curve that looks like this, right? And this is called the precision recall curve. A few things to note here again. The ROC curve was kind of monotonic in the sense it could never go back up, right? It would either go to the right or come down, to the right or come down. It could never go back up. Whereas the precision recall curve can sometimes go back up. And the reason for that is in what we are measuring is a trade-off between precision and recall. So let's imagine what happens if we were to start over here, right? Bring the threshold down. We got one example, and that one example was positive. So the precision is 100%, but the recall was 0.1. So we come to this point basically where the precision is 100%, but the recall is 0.1. Then let's say we bring the threshold down one more level. The precision is still at 100%. The recall has increased to 0.2 because we recovered 2 out of the 10 examples. And then let's say we encountered a third example, a third that was negative, right? So the recall has not improved at all because we've still recovered only 2 out of the 10 example, but our precision drops from 2 out of 2 to 2 out of 3, right? So the drops are always vertical because we come down in precision, but whenever we encounter a new example, the precision will come down, but the recall will stay the same because the number of positive examples that we've recovered is, does not change if we encounter a new negative example. So the precision recall curve has these vertical drops that correspond to encountering negative examples in our scan, right? But once we are here, let's say we start encountering positive examples again, then what we see is so we go from 2 out of 3 to 3 out of 4 to 4 out of 5. So this is like a gradual increase as we encounter more positive examples. So the precision recall curve will will have these, a pretty standard pattern of having vertical drops and slow climbs, vertical drops and slow climbs. Whereas the ROC curve will have horizontal, vertical movements. Right? And just like the ROC curve, you can also measure the area under the precision recall curve. Right? And one kind of another observation that you can make is that while the ROC curve always started at the top left corner and ended at the bottom right corner, the precision recall curve, when it reaches 100% recall, right? When you take the threshold all the way to 0, your precision, when you effectively predicted everything to be positive, your precision will be exactly equal to your prevalence, right? So the precision recall curve will terminate at the right hand side at the level equal to the prevalence. So in this case, prevalence was 0.5ish, or somewhere there, right? So it ends here at prevalence equals 0.5. That also means that there is this the precision recall curve might look something like this. So this is always the prevalence level where the precision recall curve will end. It also means that there is this kind of area in a precision recall curve, a certain area in the curve where the precision recall curve just cannot enter. Right? No matter how horribly your model ranks your examples, in the worst case, let's say your model places all the negatives at the top and all the positives at the bottom, like the worst possible situation. Right? In the worst possible situation, you're going to keep encountering negatives. That's going to kill our precision with 0 recall, right? And we're going to start off climbing the ROC, the precision recall curve, starting from the first positive example, and we're going to basically start at once the threshold comes here, we're going to start at 1 over the sum of all the negative examples plus 1. From that, we're going to move on to 2 over sum of all the negative examples plus 2, and so on until we reach number of positive over number of negative plus number of positive. It's going to be the slow climb until the prevalence level. So no matter how bad your model is, you kind of get this amount of area for free in the area under the precision recall curve, right? So there are variants of the area under the precision curve that account for this, that kind of discounts this area and only measures kind of the area that your model has truly earned, and disregarding the part you get for free. And that's something you might be kind of that's something worth knowing, right? If your prevalence is very high, then your area under the precision recall curve might look very good, just because you get a lot of area just for free. All right, moving on. Okay. So let's look at these two models, right? So let's suppose there is some data set, and we have two models, model A and model B, right? And the models A and B make predictions or assign probability values to every example. And let's say this is the plot. So model A assigned some negative example this probability value and this probability value, and these are just the probability values that were assigned by model A, and these are the probability values that were assigned by model B. Now, by just looking at this, is there a reason to prefer one model over the other? Is one of them better than the other, or does one of them look better than the other? B looks better. Okay. Anybody thinks A looks better? Why does B look better?
Because both of them are confused from the middle point where B can calculate most of the points.
So the answer was B was confusing for a few points, but it did well on this region and it did well on this region. Right? Yeah. So yeah, it might be reasonable to think B does better, and we should choose B. Now, of all the metrics that we have looked so far, which metric would rank B higher than A? None? Any other guesses? Right, that's the correct answer. None of them will rank B higher than A, because the ranking of all the points were the same. Right? All the points over here, though they were clustered together, if you just look at the ranking position of all the examples, we encounter positives and negatives in the same order. And all the metrics that we've seen so far only cared about the ranking. Right? For example, for the area under the precision recall curve, we were scanning the thresholds, but we were only making moves when we encountered the next positive or negative example. Right? We didn't care what the threshold value was. We just looked at the order in which the positives and negatives were encountered. Right? So all the metrics that we've seen so far are ranking based metrics. Right? And as we can see here are two situations which qualitatively look very different, but from the point of view of all the metrics we've seen so far, they're exactly the same. Right? And that's a kind of a motivation for something that's called the log loss. Right? The log loss is it's in fact the loss value that we use in logistic regression. Right? So the log loss is, think of the log loss as so if you remember, in logistic regression, if the true label was y and our prediction was y hat, right, the loss that we used was y log y hat plus 1 minus y log 1 minus y hat. Right? This value itself can be used as a metric. Right? So it's basically just the log likelihood of our prediction. That's also called the log loss. Right? So the log loss is kind of different from the two that we've seen so far. Is kind of different from the ones that we've seen so far, in that it takes into account the value of the predicted probability itself. It's not just looking at the relative thresholds, right? So if we were to kind of sum over I equals 1 to n, yi, y high, y hat I, right? So this loss value takes into account the predicted value of the probability as well, right? And it basically rewards confident correct answers, which means it's not enough that when you predict a correct answer with a relatively high probability, then it rewards you to take that even higher. But at the same time, it very heavily penalizes you when you get it wrong and are very confident about it. Right? So it's kind of asymmetric in the way that it rewards you for having confident correct answers, but pretty much kills you if you make a confident wrong answer. Right? And it is this property that makes the model kind of choose the actual probability value more carefully. Right? This objective does not just look at whether the positives were higher and negatives were low. It also looks into how much what level of confidence did the model assign in each of these predictions. Right? So another way to think of the log loss is you can think of a betting game. Right? Let's say you need to make a prediction of of n examples. Let's say there are n examples, they can be positive or negative, and you're going to be presented one example at a time, and you need to make a prediction of true or false. And the way you're asked to make this prediction is not just make a prediction, but you're asked to make a bet, right? You need to make a bet of some dollar amount between 0 and 1, say 25 cents or 99 cents or whatever. You need to make a bet of what the correct answer is for a given example. Now, if you make the bet, you win the bet amount, but if you lose the bet, you win 1 minus the betted amount, right? So, which means now if so let's say you have example I, xi, you need to make a bet of what is the you need to make a bet of what of how confident you are about the prediction that you made. Let's say you predict it to be y equals 1. You make some prediction, and you also place a bet. We'll call it p, right? And for x2, let's say you predict y equals whatever 0 and some bet amount p. Let's call this p1, p2. Now, if you win, you get p. If you lose, you get 1 minus p. Right? And then finally, you go through all the examples, and in the very end, what you get is not the sum of them, but the product of them. Right? So for one example, maybe you got the correct answer and you earned this value, and for another example, maybe you got it wrong and you earned this value, right? And the final take-home amount that you're going to walk away with at the end of it is going to be the product of all these values, right? Which means if for any one of the examples you predicted, you assigned a confidence of 1 or 0.99999 and you happen to be wrong, the entire product will be 0 or very close to 0. Right? So in this exercise, in fact, there are kind of studies that show that with this kind of an exercise, you can extract the true level of confidence that a person has in making a bet. Right? If you were to earn the sum of these things, then you would be a lot more. Your betting strategy would be very different. But if you're going to walk away with the product of all these values, then you know that if you make one confident wrong prediction, you assign a probability of 1 and the answer was wrong, then you get 0 and the product of 0 with anything else is 0. Right? And so that's basically how the yeah, your question.
Can you ever use this on models that directly make class predictions and not probability?
So the question is, can we use this in on models that make direct class predictions rather than scores or probabilities? No. So the log loss is for probabilistic models only.
And you're kind of discouraging your model to ever be confident of anything, right? Because the model will always stay between 0.8 and 0.2. It will never even dare to go above that because it will incur such a heavy loss if it just makes one thing. So is it a good thing to go through that?
So the question is, perhaps rightly you're identifying that wouldn't this encourage the models to be more conservative, rather than making extreme values? Yeah, the log loss can make your models more conservative, but the interesting thing out of this is that this process, this kind of a loss is a proper scoring rule, which means the predicted probabilities, from this kind of a loss will always result in, calibrated probabilities.
But let's say you want to apply a model in the financial market.
Yeah.
You would never want to go with this because in the financial market you don't get products, you get sums. And if you make one, so let's say you are making 10 investments and it makes one loss, but the 9 gives you good results, you will never be confident on those 9.
Yeah, so the question is, would this be a good metric or good loss to use, say in a financial setting where you generally take the sum of rewards rather than, yeah. So there are if you're interested, the thing to look for are robust scoring rules. And we're going to look at one in a few slides. So there are other kind of scoring rules which still give you, calibrated probabilities, other scoring rules that give you calibrated probabilities but are much more risk tolerant than the log loss, right? And you can use those in those contexts. Right? So the log loss is this kind of a loss that not only evaluates the quality, not only evaluates whether you got the answer right or wrong, but also kind of elicits the true level of confidence or the true kind of belief you have, probabilistic belief you have in making a certain prediction. So this is an example of a proper scoring rule, and we saw kind of proper scoring rules in the maximum entropy lecture as well. Right? So that's log loss, which brings us to this concept of calibration. Right? So calibration is when the predicted probabilities match the real world occurrence or frequencies. Right? So in this case, we have two models on the right over here. Right? So the blue line corresponds to the calibration curve of a logistic regression model, and the orange line corresponds to the calibration curve of a support vector classifier, support vector machine. Right? The way to read this plot is on the x-axis. The x-axis corresponds to predicted probabilities, and the y-axis is the fraction of positives in the region around this predicted probability. Right? And the bottom plot over here is just a histogram of how were the different predicted probabilities, how were they distributed. Right? And you always want to look at a calibration plot and the histogram of predicted probabilities in conjunction all the time. Right? So if the calibration curve goes close to the 45-degree line, it means when the predicted probability was 0.8, for example, then the actual fraction of examples was also roughly 80%. Similarly, if of all the predictions that had a prediction of 0.2, roughly 20% of them were the positives. Right? However, the orange curve looks pretty different, right? So for the orange curve, even when it predicted a 0.6 probability, most of them were actually positives. This means that the orange curve, you can think of it as being underconfident in some way. And even though the examples were mostly positive, it kind of hesitated to assigning high probabilities to them. Right? So even in the region where the predictions are still 0.6 and 0.7, all of them are actually positive examples. Right? So a calibration curve that looks like this. So a perfectly calibrated curve would be like a straight line. Right? An underconfident calibration curve will have this kind of an inverted S shape. Right? Similarly, an overconfident model will have a calibration curve that looks like this. Right? So this would correspond to overconfident. This is underconfident. And if it's directly here, this is well calibrated. So the few takeaways from this slide is that it's always important to kind of see these two plots in conjunction, and the way you want to read them is first make sure that your model is well calibrated. Right? If your model is not even calibrated, then the probabilities that it is predicting are not even valid probabilities. Right? And then once you know that a model is well calibrated, then look at the histogram to see if you have these nice two peaks at the extremes. Right? So that's like the perfect scenario where the calibration curve is exactly along the 45-degree lines, and the histogram, it has these two perfect two peaks all the way at the left and another peak all the way at the right. So that's the ideal scenario. However, if your model is not well calibrated, right? In this case, in the orange case, if the model is not well calibrated, then this histogram says nothing at all. It does not tell you whether the model is doing well or bad. Right? In this example, if you see, both these models have, for a chosen threshold of 0.5, the logistic regression and support vector machine have, 0.87 precision, 0.85 recall, 0.86 F1 score. They're all exactly the same, right? But the calibration of the support vector machine is completely bonkers. It's not well calibrated at all. And so the histogram does not reflect the quality of classification. Right? But if the model is well calibrated, then the histogram gives you a good sense of how well the model is separating them. So just like the log loss that we saw over here, there is this other score that you can use called the Breyer score. So the Breyer score is very similar to the mean squared error. So the Breyer score, you can think of this as sum over I equals 1 to n of all your n examples. P hat, where this is the predicted probability, right? So P hat I minus yi squared. It's just the mean of the squared error between the label and the predicted probability. This question? So it's if your model is overconfident, then your histogram will generally look like the blue one because it's assigning like really high probabilities. So the probabilities are more at the extremes. It's more confident, but they are wrong, which means they've got the orderings wrong. So over here in the histogram, the labels are not visible here, right? So this means most of the probabilities, most of the examples got this probability, but it does not tell you what fraction of them were correct or wrong, right? Whereas the calibration curve tells you what fraction of them were correct or wrong.
So it would look similar to well-calibrated.
It could look similar to, so yeah, so the histogram could look similar to the well-calibrated one. It could not. There's generally underconfident models will have more probabilities assigned near 0.5. So you'll see a bulge over here if they're underconfident, and confident ones will have more assignments at the extremes, right? What you ideally want are confident models that are also calibrated. This question?
So what was the value addition from histogram? Because in well calibrated we didn't care about it, and when it was not calibrated, it didn't tell anything.
Yeah, so the question is, why not just look at the calibration plot and just ignore the histogram completely? And the answer for that is, back in the calibration discussion, we saw how calibration does not necessarily mean accuracy at all, right? So you can have a perfectly calibrated plot, but most of your assigned probabilities might be just 0.5, and you have a few of them that are well calibrated on the other side, but for most of them you're just predicting 0.5, and that's kind of bad. So ideally you want a plot that is perfectly calibrated and also well separated and have these two peaks. So that's like a good sign. Right? So the Breyer score is basically the mean squared error between the predicted probability, right? So this y is either 0 or 1, and this is between 0 and 1. Right? So we see that even though the usual ranking based metrics are exactly the same, the Breyer score between them is quite different, right? And the Breyer score is also a proper scoring rule. So in the example one of you asked before about, you know, what if you're in a kind of a finance kind of a scenario where you want to I don't know, be more risky in some way, for example. You know, you can use, you know, the Breyer scoring rule in those cases. You know, the Breyer scoring rule also is also a proper scoring rule, which means it will value calibrated probabilities more, but it is more, you know, risk tolerant. It has other trade-offs compared to the log loss. Right? Any questions on this? Right? So basically the takeaway is that, you know, always look at the calibration and the histogram in conjunction. First make sure that the model is well calibrated. Otherwise, your predictions are not even there are not even valid probabilities. And once it's calibrated, look at how well separated they are. So you may also see the terminologies like calibration versus discrimination. Right? So discrimination generally refers to how well your model can separate positives and negatives in a ranking sense, and calibration tells you how meaningful are the assigned probability values. Right? And you generally want your model to be well calibrated and have high discrimination. All right, moving on. Right, so the log probability or the log loss can also be used in unsupervised learning. So supposing you have a Gaussian mixture model or factor analysis, right? You can use log P of x to measure your whether your model has underfit or overfit. Log P of x by itself, the raw value, is hard to interpret. You know, it's hard to just look at the log likelihood and tell whether the model is good or bad. But you can always measure the log likelihood or log P of x on your training set and on your test set and measure the difference between them. Right? If the gap between them is very large, if you have a high log likelihood on your training set but low likelihood on your test set, then your unsupervised learning model has overfit on your training data. So you want to, you know, so underfitting, overfitting, even though it's commonly used in the supervised learning setting to measure accuracy or whatever, is not limited to supervised learning alone. Right? Underfitting, overfitting concepts apply just as well to unsupervised settings as well. This question?
I guess would you try to maximize, say, like the geometric mean in that case, or is there some metric you can use to kind of determine what's a good balance between the two?
So the question is.
The log likelihoods for like your training versus validation set.
Oh, so what you want to so the way you want to so the question is you have a particular training value and you have a particular test value. How do you kind of find a balance between them? The answer is very similar to how you would do in a supervised setting. Let's say you have 85% accuracy on your training set in a supervised classification. Let's say you have 23% on your test set. Right? So what do? You go and address bias or address variance to bring the gap closer together. Similarly, you fit a Gaussian mixture model that gives you a log likelihood on your training data to be, generally they are like, like minus 2000. This is like a reasonable value for a log likelihood of a Gaussian mixture model. Let's say you get minus 2000 on your training set, and on your test set you get minus 18,000. Right? Then it probably means you have assigned too many number of clusters. You want to reduce your k value, for example, and kind of bring the two together, or something along those sorts. So yeah, so log P of x can be used as an evaluation metric to measure the gap between your training likelihood and the test likelihood to see if your unsupervised model has overfit or not. However, k-means is a little tricky. K-means does not have a good probabilistic interpretation, and it also uses fixed covariances. So with k-means, it's a little harder to measure whether it is underfit or overfit. However, with Gaussian mixture models, or probabilistic models in general, it works pretty well. Yes, question?
For k-means, can't you just take like a mean squared error, like sum from the clusters to all the points in that cluster?
Yeah. Can we take the mean squared between the centroids and the examples, so which is basically the distortion function, and measure the distortion function on the test set? You could do that, but that does not always work well. So even the distortion function can so for example, let's say you have some clusters like this, and let's say you assign let's say you assign 6 cluster centroids. So you get one. Let me use a different color. So you get this centroid, centroid, right? And I mean, looking at just qualitatively, you can tell you kind of overfit. There are actually just 3 clusters, but you've assigned 6. However, if you were to measure the distortion function, if you were to hold a fraction of them as a holdout set and measure the distortion function on the test set, they will look kind of pretty similar. So the distortion function, because it does not have this flexible covariance per cluster, right? It's hard to use the distortion function as a way to check whether you underfit or overfit.
If that is not a good measure, like the distortion function, then how do you evaluate the quality of your error?
Yeah, so it's of the k-means, it's usually you end up doing some kind of a visualization, and it's more do some spot checks to see if a few examples that were in the same cluster were meaningful or not, or if similar examples ended up in different clusters. It's not as cleanly defined as the log likelihood that you get from Gaussian mixture models. Yes, question?
So in practice, I see people doing this thing where they plot k and then use the distortion function, and then like the slope increases very quickly and flattens out, and then that's how they use k.
So the comment there was you can have this distortion versus k, and eventually the distortion is gonna flatten out, and maybe just look at it and choose some value, right? However, this requires, as I said, this is like a heuristic. You have to look at it and decide. You can't compare one scalar value with another scalar value, one on a test set and one on a training set, and declare that you overfit, right? So so measuring underfitting and overfitting is not as clean with k-means as it is with Gaussian mixture models. Yeah, but this is a commonly used approach. Yeah. Right. Moving on to class imbalance problems. So generally, if you have examples where one class is a much smaller fraction than the other, or if one class kind of dominates the other class, then you kind of call it. You say that you're in a class imbalance scenario, and a lot of the metrics that we've kind of seen today can end up breaking down under class imbalance scenarios, right? So, for example, accuracy, right? So if you are in a class imbalance scenario, and let's say you have just 1% of all your examples to be positive, and you have this blind classifier that predicts no all the time, it gets 99% accuracy, right? So having a high accuracy does not mean much in a class imbalance scenario. Similarly, the log loss, right? In the log loss, the majority class can easily dominate the assigned probabilities. So if you have, log loss can be easily So imagine a logistic regression where you have some number of positive examples over here, and you have just one negative example over here. Right? Logistic regression will place the separating hyperplane, that is the line at which the y hat is 0.5, probably somewhere over here. Right? So the majority class can easily dominate the log loss and make the separating hyperplane be placed at some kind of an unreasonable location. Right? So the log loss is also vulnerable to class imbalance. AUROC, right? So imagine, let's see how the AUROC can break down. Right? So let's say you have examples that are ranked like this. Right? So suppose you are in a fraud detection scenario, credit card fraud detection, right? You want to build a classifier, given a credit card transaction, classify it as fraudulent or not, right? In this scenario, let's say you decide to use AUROC as your metric, right? AUROC, and let's say so typically in these kind of scenarios where the prevalence is very low, most of the times you are in this kind of a retrieval scenario or information retrieval kind of a scenario where you want to, given this pool of all credit card transactions, you just want to surface the fraudulent ones to the top and act on them somehow, right? So in this kind of a scenario, let's say you have a model that let's say you have 10,000 transactions. And in this 10,000 transactions, let's say 10 of them are fraudulent. Right? And let's say 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 10. So the first 10 were all good transactions, and the next 10 were all fraudulent. Whatever, assume there are 10 here, and then you have all the good examples. So this is the first 10, the next 10, and the remaining 9,980. Right? Let's say your model ranks them in this way. Right? From the user of this model, this is a useless model because you want to act on the top most likely fraudulent. The top 10 most likely transactions to be fraudulent, but all of them over here were valid ones, right? And then comes the fraudulents, after you have an equal number of good transactions, and then you have the rest, right? Now, what's going to be the AUC of this model? Right? Let's do a quick sanity check. So we have 10 positives, so chop this into 10 intervals, the sensitivity side, and the specificity side, chop it into 9,990, right? You have 9,990 pieces here. So the first 10 were all negatives, which means, for the first 10, we get a steep drop. And then we have all the 10 positive examples, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you get a negative. And this will give you an area under the curve of 0.999 or whatever, 0.99. Maybe I missed. Is it 0.99 or 0.9? Anyway, it doesn't matter. It gives you a really high AUC, even though from the usefulness of this model, you got only good transactions flagged as fraudulent at the top. Right? So in class imbalance scenarios, AUC can also be pretty bad. Accuracy is the worst. You probably never should use accuracy when you have class imbalance. But AUC can also be fooled. And so AUPRC is somewhat more robust. In precision in these kind of scenarios, when you are interested in the quality at the top, where your focus is on the top of what you do, because you're generally not going to act on the rest at all. You're just going to do something with the top predicted examples. In those kind of scenarios, you probably want to use AUPRC rather than AUROC. So the summary is that in class imbalance scenarios, your least preference should be accuracy as the choice of metric. AUROC might be better, might not be better, because AUROC can also be fooled. AUPRC is generally more robust, but with AUPRC there are other challenges that come with it. For example, if your AUPRC curve looks jagged like this, this is pretty sensitive to the ordering over here. If your ordering is different, it might look very different, right? So the AUROC can sometimes be pretty sensitive to small changes. Yes, question.
AUPRC is still not good enough, so like what to go for? Would you want to reduce, like in your data set, reduce the number of positives and then train only on the less data set, or like somehow generate more of similar kind of negatives and then train on that some workaround?
Yeah. So the question is, can you kind of adjust the class balance by upsampling or downsampling the classes to fit your model? You can do such things. So that's actually a very good point. In order to make your model perform better, you can do all kinds of things like adjusting the class balance, upsampling the minority class, downsampling the majority class, and so on. However, when you are measuring the quality of your model on a test set or a validation set, the prevalence in the test set or the validation set should match the true prevalence. Right? Do the adjustment, upsampling, downsampling, only on the training set and not on the test set.
But then will it work like?
It could help. It's the question of whether upsampling and downsampling, will it help or not? The answer is always cross-validate and check. Right? Have a validation set which is kind of pure in the sense it has the same prevalence ratios and so on. Do whatever you want with the training set, upsample it, downsample it, whatever, but then measure it on this pure validation set which has the right or the true prevalence ratio and see if it helped or not.
In terms of metrics, you don't have anything better. That's the
Yeah, generally AUPRC is there are a few more metrics. I think in the next slide. Is it in the next slide? So probably the slide after we'll look at them. Right. So you can extend all of these to a multi-class classification setting as well. So the confusion matrix in a multi-class will be k by k or n by n depending on the number of classes you have. So in binary it was just the confusion matrix had just 4, where you had two classes. But if you're in a multi-class setting, you can have one row per predicted class and one column per actual class. Right? And then you just count, what number of class C did you predict as C and so on. And here you want your diagonals to be heavy. And the reason why the name confusion matrix is used is probably more illuminating here, because if you have high values over here, then it means the model is generally confusing class B to class D, right? So the model is confused between those two classes. That's an interpretation you can use. So some of the other metrics like accuracy can be, accuracy can be analyzed as one versus many, which means you can plot AUPRC curve for one class, right? Take all the predicted probabilities, see what probability was assigned to this class versus others. Just condense your classes into just 2. You can do that. Accuracy you can, however, get it's basically the sum of all the diagonals divided by the sum of all the elements. There are variants of the ROC and the PRC curve where there's a minor detail called micro averaging and macro averaging, and you can extend the ROC curves and the precision recall curves to multi-class setting. And you can also, there's something called cost-sensitive learning techniques, where you can assign some kind of a dollar value to each cell in the confusion matrix, and you can construct a loss function by you can construct loss functions by absorbing these dollar values or any kind of a weight into the loss function and train on them. So you can look up cost sensitive learning for techniques to do that. Right? If the cost of a false positive is a lot more than a cost negative, then you can incorporate those kind of prior information into your loss function. Right? And finally, some tips on choosing a evaluation matrix. So you will see that commonly, the problem that you're trying to solve generally fits into a few templates or few patterns. Right? So there are going to be some problems where high precision is a hard constraint, and you want to maximize the recall as much as possible subject to this high precision. So one way to one example for that would be if the action that you're going to take on positive examples or examples that are predicted to be positive can have a severe negative effect or side effect on if the example happened to be negative, then you want to have high precision as a hard constraint, which means you want to, your model, when it says positive, it has to be positive. And subject to that hard constraint, you want to improve your recall as much as possible. Right? And for example, search engine results, right? When you search for something on, let's say, Google, right? What's going to show up on the top? It better be relative. It better be correct. You may miss out a few search results, but showing irrelevant results on the top is really, really bad, as opposed to missing out some relevant results. In those cases, high precision is a hard constraint, and you want to recall you want to improve your recall subject to this constraint. Similarly, if you're writing a grammar correction software, then if you miss out a few corrections, that is fine, but making a bad suggestion is a lot worse. Right? And in those cases, you want the metric that you want to use might not be any one of the metric, but the metric could be recall at a certain precision, which means you have a precision recall curve that looks like this. You fix your precision level to be some acceptable threshold, and you measure what the recall was at that fixed precision level, and then you want to optimize your recall. Right? So this length will now be your metric, right? The recall at some fixed precision. On the other hand, you can have other kinds of problems. For example, medical diagnostics, where you want to let's say you have some kind of a screening test, where let's say it's a blood test, and if it's positive, then you want to send them to a more expensive, more accurate test. And so let's say you need to build some kind of a simple screening test. And in those cases, it would be very bad if you missed patients who actually had a condition, in which case false negatives are a lot worse. But it's okay to have a few false positives because you're going to conduct this more expensive test anyways on those whom you flag. In those kind of scenarios, you want to maximize your precision subject to a high recall. Right? You don't want to lose out patients who have a condition in the screening test. Right? But at the same time, subject to this 100% recall constraint, you still want to improve your precision because you don't want you don't want to waste the more expensive test on people who may not have the condition. So in those cases, you may want to have a fixed recall, right? Fix the recall and maximize the precision. Right? In that case, this height will be the metric that you care about. right? So you can construct these derived metrics from the precision recall curve, depending on what's important for your application. And sometimes they may be capacity constrained, right? Let's say you want among the patients that are admitted today in the hospital, let's say you want to take some kind of a different action on, say, 5 of them, because you have only 5 doctors available to say test this new procedure, for example. In those cases, K is a hard constraint. Your capacity is a hard constraint. Right? In those cases, all what matters is the quality of the top K results. Right? You want high precision in the top K. You don't really care what happened here, right? Because you have this hard capacity constraint. Even if you're losing out other positives, you don't care, because anyway you did not have the capacity to do anything about them, right? In those cases, just look at the precision in the top K. So rank your examples, just look at the top K ranks and see what the precision was in that fraction. Okay? And there are many, similar to this, there are many other derived metrics. That's something that you should think about and decide what meaningful metric, what a metric is meaningful for the application that you're doing. Right? And similarly, to choose a threshold, you're going to use the threshold that you choose for classification would also be based on this. Supposing you have a fixed recall, you want a fixed recall of certain level, go up to the curve and work backwards and see what the threshold was that got you this point. All right, that's about it for the evaluation metrics. We'll wrap up with that. Any other questions with what we've seen so far? If not, I'll be around here. Walk up and ask any questions you have, and that's it for today. We'll break.